Okay, the time is 50. So let's move to the third speaker in the section 6, thermal and design. Uh, our speaker is Prasanth Prabhu Ravichandiaran. Yeah, hopefully my pronunciation is correct. So
Yeah.
yeah, he received his master's degree in electrical engineering from University Buffalo. And in 2016, he's currently pursuing a doctor in computer engineering at North Carolina State University. He has 3 more years industry experience working in a wide variety of ASIC design for DDR or custom macro LED or for the variable AR glasses and light field disciplines, and also the Pico projector. Uh, he's currently pursuing his PD and Dr. Paul Franson's
Yeah.
group. And so his current research area includes the machine learning accelerators and 3D IC and the memory acceleration. So, Person, are you ready for your presentation? Yeah, we can see your slide.
Yeah. Can you hear me loud and clear?
Yes, we can hear you. Yeah.
Oh, okay. Thanks for the kind introduction. Good morning to one and all. And I'm Prasanth, as pointed out. I'm here to present my our work on a review paper of 3D DRAM based near memory computations. And I've been working with Dr. Franson on this particular paper. So there has been a rapid growth of data-centric application, especially in applications like graph processing, image processing, and like even autonomous self-driving cars require a lot of computation to be performed in a real-time fashion, and then like with a reasonable area and power constraints along with it. There has been a lot of prior talks that's addressing the memory walls and how it's like creating a bottleneck for this entire applications. And there's been a lot of solution that's been tried in the industry right now, and research space in the industry. And one such solution is called the near memory computation, which is basically trying to move the computation as close to the DRAM or your larger memory as possible. And as pointed out by other speakers in the session, pretty much for any neural computation, the 90 to 95% of the overall computation that happens in that is essentially down to a matrix vector multiplication and accumulation operation. So it is predominant for any of these accelerators to target this particular MAC operation to be optimized as much as possible, so that like even if you over here, you could see the Iris, the version 2 that they have released. Even for computing a smaller 1 bit of a matrix output image, you have to perform like R cross C cross R into H cross H. That is a lot of computation to, with the matrix multiplication needed to be established, and then the final activation is computed. So this points out the bottleneck in the process. And in the industry, there's been like a lot of terminology that is being used for referencing these memory accelerations. Predominantly, they are processing in memory or compute in memory, pointed out by the previous speakers. And what we classify as a processing in memory, or like if the memory cells or the peripheral circuits are being modified in any shape or form, or like trying to exploit the parallelism, or trying to exploit the basic computation using an analog nature of these memories, are being considered as a processing in memory in our paper. So predominantly the non-volatile memory technologies would use these kind of analog natures and try to accelerate the computations. And the other form of the technology that has been in there is the called the near memory computation, which is basically building a logic die on top of a logic die and having a traditional DRAM memory, or like a 3D stacked DRAM along with it, so that like this is much more in a conventional format, and this would be implemented more in a volatile memory technologies like SRAM or DRAMs. And especially the 3D DRAM based near memory computation is a true enabler of this particular process, basically giving a wider like 3D logic base with a TSPs gives you a wider bandwidth, and then like reduces the data movement power. Everything is like a win-win scenario for these technologies. And here's a small depiction of like a NMC implemented with the hybrid memory cube. So over here, you could see the memory dies are being stacked on top of a wall controller, which is like basically a logic base. And then it is being closely coupled with the processing engine elements in order to compute the basic Mac, like a Mac operation or some of the specialized computation that is required for your workload in a sense. And this is a snippet of one of the processing engine that has been developed at NC State by a previous alumni called Suman De. And this would give you an overview of like what are the special operation that is being handled by the Mac, handled by the processing element, along with like some inbuilt memory in order to exploit the data reuse of the temporal data that is being used. So coming to the main concepts of the review paper that we have done, we have tried to classify the prominent structures that's available, prominent memory accelerators available out there with a few of the key parameters. And the primary parameter that we used is to have a volatile versus non-volatile. The volatile would comprise of the SRAM and DRAM based architectures, and the non-volatile would comprise something like resistive RAM and MRAM kind of architectures available out there. And we also looked at the logic implementations, how to differentiate the different architecture with their logic implementations. So any ASIC implementations, and we have classified in 3 formats. The primary one is like the ASICs, which are designed for a specific workload scenarios, so that they can, with a finite set of instructions, so that they can closely integrate and achieve higher performances. And processors-based applications are generally implemented to give a bit more flexibility for future updation of the algorithms, or a bit of reconfiguration available for the end user. And finally, we have FPGA-based implementations, which is gives you a good trade-off between the other 2 implementations, and also it's much more effective in getting the time of development, and implementation is much more faster in a sense. And also we looked at the way the programming engines or the processing elements being interconnected. So that is being classified with the programmability of the PE. So there are like different NOC architectures that is being proposed for interconnecting all these processing elements, and they have basically fall under these 3 categories: either having a fixed structure, which is like a specific instruction that is used to route the data between the different processing elements, or have a bit more flexibility for the user with a programmable unit like ASIP with a SIMD, or those kind of applications are used in order to configure the router a bit more better for different workloads in a sense. And you also have like some architectures employing like reconfigurable units, so that like they can update this via like a FPGA or router basis in a sense. And finally, we have just mentioned like the application that these architecture try to work with. And here's a table that's capturing some of the prominent NMC architectures and their memory types, and like the implementation as pointed out in the previous slides. We'll be discussing about what it relates to performance, and how these architectures stack against each other in the upcoming slides. So as pointed out earlier, like these real world applications require the area and power to be in a reasonable fashion in order for this to be a viable solution. So first we take a look at all the, we have just tabulated all the areas for the different architectures and also the power that they consume for a particular workload. We try to normalize these as much as possible against a 28 nanometer node, so that it's a fair comparison between them. And the performance that we took is measured in the form of gigaflops per unit, and the flops that we use is a 16-bit Mac operation, as that is the primary workload for any neural network or most of these applications. And finally, we have combined all these metrics in order to find efficiency for all these architectures to give a better picture of how these architecture are being designed, and what sort of application would be better for these And in this efficiency, I have classified like two parts. One is the power efficiency, which is measured as gigaflops per watt. And there is a second efficiency, that is area efficiency, which is measured as a gigaflops per millimeter square that's available. And this is the table that captures all this stuff. Rather than looking at a bunch of numbers, I've also established a graph, which will be in the next slide, which gives you the better trend of all this. So the numbers that was published in the previous slide are compared against a base GPU architecture with the same base workload that's been run on it, so that this graph is basically how much improvement you get for each architecture that's available out there over the GPU. So there's like a few trends you can clearly point out, like the multi-ANN developed at NC State has a better clear advantage on some of the area efficiencies, as it has a ASIC implementation which reduces with a reduced set instruction in order to get a better efficiency of area. And you could also see the Iris V2 has a better power efficiency. This is down to the architecture employing a large array of memory SRAMs are treated as a global buffers, so that they minimize the data movement and reduce the power related with it. And also on the other end, you could see some of the architecture like the PIM offloading, which doesn't really give you a huge benefit over the GPUs, but like probably these are designed for a larger set, and they require reconfigurability has a higher priority rather than the performance. And for all the advantages that we see with the NMC architectures or any memory acceleration, there seems to have some sort of a challenges that needs to be addressing. And we have looked at the prominent challenges and their potential solution to be addressed for, and that will be in the upcoming slides. One of the major challenges that we figured out is the data management. Basically, the way the data is partitioned across the memory, as well as the reuse ability of the data is much more critical for getting a higher efficiency of the NMCs. These is typically challenging for any neural workload or like any varying workloads, as will be shown in the next slide. So in here you have like the data, the weights of the data being spread across multiple DRAM cells, and you could see like on the feed forward, it's feed forward path of the neural network. It's in a row major, which is much more efficient for fetching. But during the backward propagation, this becomes a column major fetching. So each time it would incur a lot of latencies in order to fetch the data. So that is what we see a huge area would be to target this particular challenge and effectively manage the data across the cell in order to maximize the throughput. The other challenge that we also figured out is like some of these applications rely on the strided access or having a prefetcher that fetches the next needed data. So in here, you could see like at time zero, slice zero, you have these parameters, and T1 has like these weights are being fetched, and they use an onboard cache or like some sort of a memory to accelerate these technologies. But like what we have figured out for a sparse neural network or like some of the non-strided accesses, this might have a huge penalty in the if the prefetch is a miss, and you have to basically remove the data from the prefetcher and bring back the required data. So that would lead to a lot of unnecessary movement and would degrade the performance a bit more. The one of the exploration that we think would be possible is to have a smart prefetcher which would predict the access patterns rather than having it hard coded or like having an instruction that's been sent over through ISA. This would be a better implementation for varying workloads. And as pointed out by the previous two speakers, and the thermal challenge has become pretty much a bottleneck for all these 3D implementation. And here's a paper presented by Nai et al. Called the Cool PIM. This shows the graph for like how consistent 2 operations per nanosecond would lead to a chip temperature of more than 85 or like 85 Celsius or something like that. And like as pointed out by the panelist in the previous sessions, the requirement for the current mobile edge neural network applications are well beyond these parameters. So there has to be a way for us to so the one of the opportunities that we can think of is like a load sharing mechanism, which is basically moving the data away from the hotspots and trying to spread across the entire chip. This would be also looked at from the architecture point of view rather than from just from the thermal cooling point of view. This would be a huge opportunity in a sense. And also like as some of the graph processing or like scaling well beyond the traditional DRAMs, and they require a lot of other to be having connected in a network fashion. And here's a paper that's published by which has like SMCs, which has basically like four NMC cores being connected together with the networks. One of the things that we looked at is like if the data partition that's pointed out earlier, if it's not partitioned well across the different NMCs, and if there's data sharing between the two of these cores, this tends to have a bottleneck again back to the links that's available out there. This is a tricky challenge, and this would be addressed in two different ways. One could be having a programmable network adapter, and also having an architecture that can share multiple maybe having a hybrid architecture that can share the data parameters between the two cores wherever they are sharing, rather than just having it exclusively at one place. And there are some of the minor challenges that's been also pointed out in this paper. Most of the NMC architecture or the PAM architectures out there, they treat their instruction that is specific for their acceleration as exclusive, and any memory bound instruction that is being sent out from the CPU is being either delayed or like completely neglected. This would become a problem if you're trying to get it into a mainline processing or a CPU available out there. And there is a potential for looking at offloading a bit more, as pointed out earlier. Like some of the offloading has not been hugely beneficial. So like maybe for temporal data that is beneficial from having a cache-like structure, you could try to offload it to the CPU rather than trying to run it on a memory core in order to reduce power. So these could be looked at as well. And final few things are like traditionally there is not a standardized workload that has been established in the industry for measuring all these different architectures or all these different designs that's out there. So we would propose to have some sort of a standardized architecture, standardized workload, so that like we could replicate what they have actually done and try to figure out whether the newer designs stack up against each other or not. And some of these NMC or a PIM instruction has to be generated from the host end, and that has to be mitigated by having a smart system which can decide what kind of instruction needs to be decided. And some of this is being addressed at NC State prior works, where some of the SIMD operation has been streamlined within the core in order to get it better speed and other stuff. And finally, I would like to thank Dr. Davis and some of the NC State peers and also Qualcomm for funding this research. Thank you. I'd be happy to take any questions if you have.
Thanks, Prasanth, for your nice presentation. And yeah, if you have any question, please feel free to unmute or put it in the chat.
Yes.
In your analysis and comparison of power, did you include any architectures with RRAM, not volatile memories? Did you see any power advantage to?
So the question was from Dr. Davis. So basically the question is whether any RRAMs or other non-volatile or architectures are being used for comparison for power and other stuff. No, we looked at only at the 3D DRAM based architectures, not non-volatile. So only the volatile memories has been looked at this.
Thank you for the question. So any questions?
Hi, I had a quick question.
Yeah.
Can you hear me? Okay.
Yes.
Yeah.
Thank you for the nice talk. I was curious, since DRAMs inherently might be or are like lower speed and less power efficient compared to, let's say, even on-chip memory or some of the emerging devices. So what kind of applications can we have will benefit most from near memory compute or in-memory compute using DRAMs? Maybe you touched upon this, but if you could just comment.
Yeah, sure. So when we say about DRAM, this is referring to the 3D stacked based DRAM. So some of the 3D DRAM has a higher bandwidth available through all these TSPs. So basically what it does is has a vault which has localized memory arrays, and so that the access time and everything is much smaller rather than passing the entire DRAM. And these individual structures over here in this example, you could see there's 32 different vault, and then you have 4 different memories stacked on top of each other, and each vault is controlled by its own vault controller. Basically that's equivalent to your memory controller, DRAM memory controller. And these processing engines are closely coupled with them, so this exposes a higher bandwidth than a normal traditional DRAM. So you're looking at a bandwidth of either for a HMC it's about 320 gigabits per second, and for a newer versions it's much more higher. So we are targeting in that range, and in order to look at the applications for neural networks and other places. From compute in memory point of view, I think their application space is slightly different because they are slightly more they consume a bit more area and they have less density compared to these solution that we put together here.
Thank you.
Okay, thank you. Any questions? Yeah. So I don't see any question from the chat, and so if not, yeah, that's thank you.